Welcome to recording 1A in a series on linear inequalities in two variables for Unit 9, Chapter 9 of Mathematics 2200. We'll be looking at explaining when a solid or a dashed line should be used in the solution to an inequality that's in two variables, explaining how to use test points, and sketching the graph of a linear inequality, again in the context of two variables. So quickly, what is a linear inequality in two variables? Well, basically, it's like a linear equation. It's just that it involves a less than sign, a greater than or equal sign, or a greater than sign. It can be written in any of these forms, but it doesn't have to be, as long as it's a first degree equation. So for example, this one is in the form ax plus by, because it's got a negative 3x plus 1y and a c value over here. But this one's just been rearranged. Next, what does it mean to solve an inequality in two variables? Well, I've got two inequalities set up here, y greater than or equal to 5x minus 3 and y greater than 5x minus 3. We're going to substitute each of these points, x and y, into each of these inequalities to see if they satisfy. So when I put the 0 and the 5 in for x and y here, I've got 5 greater than or equal to negative 3. That's true, so yes, it does satisfy. And meanwhile, over here, 5 is greater than negative 3, so that's also true. So it didn't matter in this case about whether there was an equal sign or not. When I substitute the 1 and 2 in each of them, in the first case I get 2 greater than or equal to 2. Write that over here. And yes, 2 is greater than or equal to, so that's true. Meanwhile, in the other one, I'll get 2 greater than 2. That's false. Now when I put in 0 and negative 3, I get negative 3 greater than or equal to negative 3 here. I'm going to put them in, so that's true. But over here I get negative 3 greater than negative 3. That's false. For the next one, when I substitute 8 and 36, I will wind up with 36 greater than or equal to 37. That's false. Of course, if it's false there, it's going to have to be false over here. For the last one, if I put in negative 2, negative 13, I wind up with negative 13 greater than or equal to negative 23, and yes, that's true. And of course, it's true over here. So as we can see, there are some points that will be true in both, some points that will be false in both. But points that make this inequality true because of the equal sign will make this one false. Obviously, there are an infinite number of points, x and y, that we could put into an inequality to satisfy it. How do we show that on a graph? Well, we do it by showing the shaded region that contains all those points. The other thing we do is, if the point is included on the boundary, if there's an equal sign, like this, we'll have a solid boundary. And if there's no equal sign, it will be a dashed boundary. Now let's take a couple of these points, and well, 3 of these points, and see which inequality they satisfy. So I've set up a table here. My first point is in the shaded region for both graphs. Let's see what happens. I wind up, when I put in the 7 for the x and the 2 for the y, I wind up with 2 less than or equal to 13, and over here 2 less than 13. Both of these are true, and as they should be because they're both in the shaded region. Let's do the next point. Well, this was a boundary point, and in the first case, it does satisfy because of the equal, so that's true. 5 less than or equal to 5, but over here I get 5 less than 5. That's false, because we're missing the equal sign that would make it true. Now, for our last point. When I substitute in the values for x and y, in the first case I get 4 less than or equal to negative 11. That's false. And of course 4 less than negative 11 is also false. Let's bring these ideas over to an example. We want to graph the inequality y greater than or equal to negative 2x plus 3. We start with the boundary, y equals negative 2x plus 3. This one has a y-intercept of 3 and a slope of negative 2, so I'll go down 2 and over 1, like so. Get a few points for some accuracy. Now we also have to determine if the boundary should be solid or dashed. It's solid if there's an equal sign, because that includes any points that are on the line that will make that true. So we've chosen a solid boundary. Now we just need to know which way does the shaded region go. We do that by using a test point. Take any point, it does, as long as it's not on the boundary, because the points on the boundary aren't going to tell us anything in terms of which way the shaded region should go. I'll choose 0, 0, nice and easy. So I'll substitute it into my inequality, and I get 0 greater than or equal to 3. Because that gives us a false statement, it doesn't satisfy the inequality. Our test point, 0, 0, is located right there. It's not in the shaded region because it doesn't satisfy, so we shade the other way. So I just use my highlighter. You can use the side of your pencil to do your shading. It's not a work of art, just do a reasonable job. One last example, graph 2x minus 3y less than 6. My boundary is 2x minus 3y equals 6. I'll find the x-intercept by putting in 0 for the y to get x equals 3. Now I'll do my y-intercept by putting in 0 for the x here. And so I get negative 3y equals 6, y will equal negative 2. That gives us enough points to sketch the boundary, although I can get more by going up in the same pattern, up 2 over 3, up 2 over 3, gives me another point for accuracy. Now I've drawn in my boundary, but I've got an error. Should it be solid or dashed? Well, there's no equal sign, so it should be dashed. Now we need to choose a test point. Normally I would choose 0, 0 here, and you should too probably. But just for the heck of it, I'll choose a different point, like 2, 2. I like to choose points where the x and y values are the same, so it's hard to mix them up when I'm substituting. So when I put in positive 2, I got negative 2 is less than 6. That's true. Therefore, my test point must be in the shaded region. It's a good thing I didn't have to graduate high school based on my artistic ability. Key ideas. A point satisfies an inequality if it makes a true statement. An inequality involving a less than or a greater than will require a dash boundary. An inequality involving a less than or equal to or a greater than or equal to will require a solid boundary. And here are the steps we followed for graphing an inequality in two variables.